and complexity. But then I also wrote in gravity. And we will see how much time we have really for that latter point. But let me start now by just giving you like a mind map of the kind of topics that are interesting in the context of these three words. Of course, not all of them, by far not all of them, I'll have the time to cover this week. But it's probably still good to know roughly or to have an idea of how these things relate and what might be interesting areas to look into. So we have at the center, we have, of course, our notions of chaos and complexity. And let's make a bubble around it. But they are linked, I mean, very clearly to ideas of thermalization and ergodicity, which have already been mentioned. So there's some link. In that sense, they're also related to the question of how we're supposed to think about the applicability and the emergence of statistical physics. Okay, and there are some relations like this. They are, to the topic also of this school, the other topic that is in the title of this school, they are related in some sense to integrability. But in the sense that in some way integrability is the mortal enemy of chaos, or the other way around. Sorry, I have to tie my shoelaces. Excuse me. In some sense that one way of saying what actually makes a system chaotic is to say, well, it's all those that are not integrable, which do not lead in the strict sense to a notion of thermalization. Those are the systems which are very special, and one would like to say that the generic system is rather not integrable because it needs an extensive number of conserved degrees of freedom, of conserved quantities. So the generic system which does not possess them has more like the phenomenology of chaos. But of course, because you define them in sort of, let's say, competition to each other, it is extremely interesting also to study integrability if one is actually interested in chaos. And maybe even more interesting in some sense because it's sort of leads to very beautiful developments is to study the boundary between the two. And in some sense, what you've heard earlier today already is a system that is sort of kind of there, but perhaps sort of in the middle. Okay, so now well, another set of topics that people are very interested in and in which this ideas of chaos and complexity turn out to be quite useful is quantum computation, quantum computing, and also the idea of quantum simulation, which is the both theoretical and experimental effort to use modern quantum technology to control and study more and more complex quantum systems. Very good. And then the thing that I am personally most excited about in terms of chaos and complexity is, physics of black holes. So let me put black holes here. Okay. And the idea why chaos and complexity might be applicable to the study of black holes, the simplest way, and I'll say more about it, well, I hope, as I said, if I have the time, is that black holes really in the context of gravity more generally are the representatives of thermality, of thermal states. And as such, they are intimately linked also to the idea of chaotic dynamics. For example, we can study their formation and eventual evaporation as a chaotic process. And complexity, well, that's not very obvious at the moment why, but it also has a large role to play in the study of black holes nowadays. Finally, it could have been part of this bubble here, but I do want to mention also just the idea more generally of quantum gravity. And well, yeah, let me just write it like this. I was going to write low-dimensional quantum gravity here, but let me just say, generally speaking, even in physical dimensions, it is now a well-studied subject to think about chaos, but especially also about complexity. And so obviously these are connected, these are connected, this is connected. There are many interconnections which maybe we can explore perhaps as part of questions as these lectures go on. But the actual plan of these lectures, and again, I'll probably have to adapt depending on how much time I spend on aspects, but is to first spend some time, maybe the first 2 lectures, to introduce to you the notions of chaos and the notions of complexity as they relate to many of these topics, but in particular to black holes and quantum gravity, although I will not mention that in the first 2 lectures, and then hopefully use the remaining time to make those connections more directly. And in the background of many of the things that I will say, we do have the ideas of the emergence of statistical physics. We will talk somewhat about thermalization and ergodicity, probably not so much about this aspect, although I'm also actively interested in that. So if you have questions, you can also ask me in private. Okay, so this is sort of like a mind map to keep, maybe also here in the center. I will now try and go into the actual lecture. So as an introductory topic, let me talk about, or let me mention just a few words about what actually chaos is supposed to be. And I will start by saying a couple of words about classical chaos. That's, of course, a subject that many of you will be familiar, either from undergrad, like a dynamics course, or from postgraduate courses. So I'm probably just telling you things you already know. But roughly speaking, the idea of classical chaos is encapsulated in what people like to call the butterfly effect. And the butterfly effect is just a everyday language way of stating the fact that a system that is chaotic is supposed to exhibit exponential sensitivity to its initial conditions, to the initial conditions. Okay. So the idea, of course, for the name is that if a butterfly flaps its wings here, because the climate, or let's say the weather, is such a complex, chaotic system, it could have massive effects, such as causing a typhoon in the South China Sea, or something of that sort. Now, more technically, though, of course, if we look at phase space, so if we look at all canonical momenta and all canonical coordinates, then technically speaking, or sometimes I will refer to the phase space as omega. Phase space, I can even write it. Okay. Then the idea is that you look at, let's say, some initial condition x0. So this is just some point that has like all momenta and all coordinates specified. X will be the vector of all p's and all x's, and that will define some trajectory just by, let's say, solving the equations of motions, or more technically by following the Hamiltonian flow. And then you might want to compare it to some nearby initial condition, which is x0 plus delta x0, which will also lead to some trajectory. And the idea is that if you look at the trajectories at some later time, so this might be x at time t, given that it started at x0, whereas this is x at some time t, given that it started at x0 plus delta x0, then this exponential sensitivity is encapsulated mathematically in the fact that the distance between these two trajectories, so delta x as a function of t, exponentially amplifies the initial separation that was present, so this x0, delta x0, okay? And the characteristic exponential rate with which it diverges is called the Lyapunov exponent. Now, of course, there are many directions in phase space. So there are potentially many different Lyapunov exponents. And in fact, this does lead to the idea of a Lyapunov spectrum. But for many of the most prominent manifestations of this chaotic nature of such systems, it's actually the largest positive, the maximal Lyapunov exponent that counts. So we can, in some sense, redefine that as the Lyapunov exponent. Okay, so examples of such systems, I mean, as I just suggested, they abound because I made the claim that this is the generic behavior, unless you specify something very particular about the system, like it contains a lot of symmetries. But of course, if you want to talk about genericity, you get into the issues of how do you define that mathematically, and you get into things like measure theory and so on, which is definitely not, well, first of all, my daily bread and butter, but also it's just not the point of these lectures. But let me give you instead some examples. So I'm just going to mention them. I was told also by the organizers that there are going to be some example sheets, so I might put some of these examples on those sheets. So one that's very simple goes under the name of the logistic map. And as I said, we'll look at it as an exercise. So this is actually just to say, you can also play these games, literally like you can play games. Here we have continuous dynamics, but you could, of course, also make up some rules which go discretely. So you can apply them once, you can apply them twice. It's like, playing a game of cards. After one round, you apply the rules again. The logistic map is such an example. I personally have never really had a reason to use it in my research, but it is in a system where you can actually calculate the Lyapunov exponent analytically, which is extremely rare. So that's why I put it on the example sheet. The second example, that's something, a computation that I hope to go through with you, is a black hole. So you see I'm already pulling out two very, very different, this we will actually do probably in the class. And then there are, things like, I don't know, the weather. So I think in the weather, the simplest system set of coupled nonlinear ODEs is known as the Lorentz system. They have to do with the weather, and there are many others. I should say, just to be absolutely clear, what we're going to calculate in the context of a black hole is actually something that's more like a quantum version of this Lyapunov exponent, which some of you already evoked, but we'll get there when we discuss it, okay? But, okay, so there are many, many examples of this. But what does it actually mean in terms of, systems that exhibit these properties in terms of what is the physical manifestation of this? And I've already suggested that one of the physical manifestations is that this leads to thermalization and, in some sense, gives us a reason to apply statistical physics to thermal systems. And so the way that proceeds, just to give a sketch, is that you would start, again, with phase space. Of course, should be a higher dimensional phase space, not two-dimensional. I'm just drawing it two-dimensional because we have a two-dimensional blackboard. But you will start with something like an initial distribution on phase space. So you have some area here in which you specify some phase space function, or you could just give the density in phase space and make it uniform here and zero everywhere else. And this is what you would call your initial state. And then what happens is that, as I said, as we have seen, there will be these positive Lyapunov exponent, one of which will be the largest. And so in that direction, the system expands obviously exponentially faster than in all other directions by definitions. So as time progresses, this initial blob will have a tendency to elongate in one particular direction. It will become some sort of wormy structure. And I should also say that, let's say, in a system where you have conserved energy, which is most of the time what one might be interested in to look at, you might also say that you're actually on an energy shell in phase space, meaning on the locus in phase space that corresponds to a given fixed energy. So this expansion also has to respect, that it has to stay on the same energy shell. And what happens once it sort of wraps once the linear extent of this energy shell, let's say it's a compact energy shell, then it will be difficult for you to make any statement about where it actually came from, whether the blob was like here or here or here, because it will elongate anyway into the same kind of worm-like structure on the energy shell. And so this means that it, in an operational sense, forgets about its initial condition. And this thing here, I'm just mentioning this because that's something that we're going to actually mention every now and then as we go on. This is sort of like a classical version of what we will later call scrambling type behavior. And the scrambling type behavior actually is linked to the Lyapunov exponent because, as we just argued several times, the way that it elongates in one direction very drastically is the direction of the maximal Lyapunov exponent. Now, this now goes on. Of course, we should also say that maybe my drawings aren't that precise, but if they were, they should be respecting Liouville's theorem that the actual area will be conserved. Okay, so this thing really become a long and very thin worm the more it expands out. And so what it does eventually is that it will sort of wiggle around phase space in some non-self-intersecting way, become a very intricate kind of worm along phase space. Maybe let's make it just a little bit wider. And if you just squint your eyes a little bit, meaning that you maybe coarse grain a little bit with a small, let's say, smearing parameter, you will find that it actually uniformly explores the energy shell that is available to it in phase space. So time progresses even more, and this leads to the idea that you reach some sort of global thermal state also is related to the notion of ergodicity and mixing, which are other important aspects of chaotic dynamics. And so at the end state that you have is that the system, in some sense, is well described by an ensemble average in the following sense, namely that if you take any function on phase space f and you evaluate it along p of t, q of t, and then time average it, okay, this is going to actually become equivalent as time becomes very, very large. So let's say time tends to infinity to an average of the same function, p, q now, averaged in some ensemble. And of course, the point being that if you have a system that actually possesses a thermodynamic limit and that you want to think of as thermal, then in the thermodynamic limit, we can write something like this. We can write that f of p of t, q of t, time averaged actually approaches, for example, f of p q averaged in the microcanonical ensemble, which has the same energy that I was remarking previously. So this could be, for example, a microcanonical average. Of course, proving such things for any given system are usually actually forbiddingly complicated. But I did want to say that I want to lay down this idea in this sort of sequence of thermalization currently in the classical context. So because I wanted to make the point that indeed chaos, and this will also be true in the quantum case, but we will get there, but the chaos is really intimately linked to the idea of ergodicity, but also thermalization. And this is something that we are going to encounter precisely in many contexts, but in particular, for example, in this context of black holes and gravity. And I seem to, by the way, switch between American and UK notation. So yes, I apologize for that. Okay, so, and of course, okay, the idea here is this idea of ergodicity, namely that time averages are the same really as ensemble averages. Or, I mean, take, the system by its own intrinsic dynamics moves in a state in which time averages are the same as ensemble averages. Okay. Now, I will say one more thing about classical chaos, then we can maybe discuss, and I will try and go to what really is the main point of my lectures, which is actually quantum chaotic systems. But there is one thing which is sort of like basically just an informal observation, which is that we can just go back one more time to this Lyapunov. So let's say Lyapunov again. Okay. So like if you, so here I wrote it as something intrinsically written on phase space. And you can see that the way to really define, one way of defining it mathematically would have been to linearize the dynamics on phase space in the delta x0, for example. And then, that would give you some kind of a matrix of derivatives, and you could extract from this matrix of derivatives in a limiting process this Lyapunov exponent. But a more informal way of doing it, which also is, if you want, well-defined on phase space, but it just says that if we look instead at something like the Poisson bracket between P and Q, Q and P, I guess I wanted to write. I mean, both work, but I wrote Q and P. Okay, then this gives me just dq of t by dq, dp by dp. And therefore, we can think of this, we can identify here the derivative of the trajectory with respect to half of the initial condition. And this also then should exponentially diverge in a system that is Lyapunov unstable, or in a system that has one positive Lyapunov exponent. Okay, so we should think of this as, yeah, fine, that's all good. And so it's also, in some sense, the Poisson bracket can help us to take this derivative of the flow with respect to the initial condition. But so that's actually interesting because it associates the Lyapunov exponent to a property of a Poisson bracket. And this will be useful once we pass to the quantum limit. Once we pass to a description of chaos for quantum mechanical systems. But as I said, I mean, I think this is an informal observation, and even actually when we go to the topic of quantum chaos, we can actually motivate the existence of some kind of generalization of Lyapunov exponents without necessarily having to look at a Poisson bracket and particular operators. But we'll make those remarks when we get there. So this is everything I wanted to say about classical chaos. It's really a lightning review, but it allowed me to give you the main message, I think, which is that chaotic systems are those that are not integrable. I didn't say that, but well, I said it once. So I didn't particularly make the point later on, but that's something to keep in mind. That chaotic systems are, in some sense, those that thermalize, but also that the mechanism of thermalization and also the different hierarchies of chaoticity and thermalization are actually very interesting and can be very rich in this classical context. And one might want to imitate what happens here for quantum mechanical systems, which is what I will turn to next, except that I should already say the disclaimer. I set it up like this, but actually it turns out that trying to imitate what's happening here in the context of quantum mechanics is not the way forward, is actually much more subtle than you think. And actually the way that we think about this complex of ideas in quantum systems actually has, at least at first sight, a very different flavor to it. But it's also a good time to take a little break for questions. Yes?
Does that statement imply that classically chaos is the only mechanism for thermalization, or are there other mechanisms possible?
You mean whether systems might thermalize, like you mean whether systems that are not chaotic can thermalize?
Or that is both as necessary and a sufficient condition?
No, it's not. And it's because so Lyapunov chaos is not both necessary and sufficient. It's not sufficient. It is necessary, as far as I know. But you need to also put in things like mixing behavior, for example, to really get to a thermal state. And the mixing behavior, I didn't define it somewhat on purpose because I didn't want to enter too much into the details. But for example, you could say that correlations evaluated along the phase space flow decay, in fact, typically decay exponentially. Yes?
There are systems which are mixing but not chaotic in quantum sense, so it's not even necessary.
Right. Good. Yes.
So like
Yes.
billiards, polygonal billiards.
Indeed. Yeah.
They will be mixing. Mathematicians cannot do that, but they are not together.
Yes. Thank you.
I didn't fully understand. Can you explain again why in your notation the Poisson bracket of Q and P is like time dependent, not just one?
Well, I can put in here any function that I want, and I can put in the trajectory. Sorry?
So it's a generic function, not
Well, I can call it Q of t if I want to. Yes.
okay.
Yes.
I want to ask a small question about the future because you mentioned the black hole several times, and I want to know, does it mean that a theoretical gravity theory means that you need to have a black hole?
Say again one more. I didn't understand actually the question. Can you speak up a little bit, please?
Because you mentioned the black holes several times, so I just want to know, does it mean chaos in the gravity side always means that you need to have a black hole, or other kind of gravity background also has this kind of things like?
That's a good question. So the black hole is basically the same as the thermal state or the thermal ensemble in this discussion. Well, with some caveats. So it's sort of like the end state of the evolution, but of course you can have properties, you can see properties of chaotic dynamics even before the black hole is there. There are actually some cases also where you're like below the black hole threshold and you get just thermalization of, let's say, a gas of gravitons, which also has chaotic dynamics. But in the overwhelming number of examples in gravity, this will somehow involve a black hole. Okay, anything else? Then let's go to quantum. So this actually, one talks usually about spectral notions of chaos. One typically talks about things like the so-called eigenstate thermalization hypothesis, but also one might talk about something that makes more close contact to what we just discussed, which is this OTOC type chaos. OTOC stands for out of time order correlation. It is something which will encode a quantum version of this Lyapunov exponent. Now, well, we should, of course, examine properties. We should focus on what we actually have at our disposal, namely the Schrödinger equation itself, time-dependent Schrödinger equation. And we should also look at properties of observables in quantum mechanics, which are, associated to operators in states rho over this quantum system. So rho, of course, could be a pure state. It could be a mixed state. It could be a non-equilibrium initial state. It could be a thermal distribution. So what we have at our disposal is basically things that are very different from the notions that we just discussed. Namely, we have the spectrum. So we have, the various states. And I mean, just for simplicity, I guess I'm already pretending that everything is discrete. And we have the associated eigenenergies. And then we also have, let's say, matrix elements, for example, in this basis of operators. So we would have A, I, J. We would have, I suppose, B for some other operator, and so on. Nothing that looks particularly like anything that we have seen here. So the way that one usually thinks about chaos in quantum systems, well, I don't know if this statement is maybe correct in full generality, but I was going to say should base itself on these notions. And so there are two main paradigms that I want to mention right now. I've already started mentioning them by saying we talk about the spectrum and we talk about this ETH thing. So the first paradigm of quantum chaos that I want to introduce is the so-called random matrix theory paradigm. So this is RMT, random matrix theory. Okay. And this was actually already invoked a couple of times in the morning lecture. So the idea is we make statements about the spectrum of the Hamiltonian of a chaotic system. And the idea is that let me first give the definition and make the statement, and then we'll argue a little bit about what it really means physically. So RMT basically you should think of as integrals over matrices. Or maybe also you can think of it as something like a non-commutative version of probability or matrix-valued probability. So what that means is that if we write, for example, we're going to examine quantities such as the expectation with respect to a matrix-valued probability distribution of some function, or we might even say operator A RMT. So M here is a matrix, and A of M is the observable. Of course, what I will really do is I will integrate over the matrix with some appropriate measure, dm. And the measure often is written like as e to the minus trace of a potential of this matrix of this A of M. So, it doesn't really depend on M here, but I'm just saying that A is some observable that we're interested in, and this is sort of like the matrix probability measure. So, of course, an important aspect of this is that we need to figure out how do we think about this matrix probability measure. And also, if this were a course more on the matrix model aspect of chaos, or even more generally, we would have to spend some time on actually understanding how we deal with such systems, mathematically even. But right now, I just wanted to flash that. So in RMT, I will now, of course, talk about how this relates to quantum chaos. But RMT is actually just the same as rules for taking integrals over matrices, which allow you to give you some sort of ensemble averaged quantities given observables that you put in. Now, matrix models also have a life of their own in theoretical physics, by the way. And this is not totally unrelated, actually. Because, this actually I wanted to leave up. Why not leave the mind map here? They also have a life of their own because they are almost like toy models of very simple quantum field theories. I mean, it's not quite a path integral of a quantum field theory, but it is also no longer an integral just over numbers. And that's actually a beautiful field with many links also to mathematical physics and geometry. Okay, very good. By the way, I started at 11, is that right? Yeah. So, for example, my colleague Marcos Marinho has written a very nice set of lecture notes on this aspects. There are, I think, the Lesouche lecture on matrix models. But typically here, so for the purposes of talking about chaos, we will think of this matrix M as the Hamiltonian. And we will think of it as, let's say, a D by D matrix, where D is either the dimension of the Hilbert space if we're in a finite dimensional system, or it will be effectively the dimension of the Hamiltonian once it is projected onto, for example, a microcanonical window of states if you're in a more complicated context. So this is the Hamiltonian. So if I take an integral over a matrix-valued probability distribution where I think of the matrix as being the Hamiltonian, what I'm really doing is that I'm averaging a given quantity over all the possible choices of Hamiltonians that will be restricted by some symmetries. And I'm sort of, in that way, giving an ensemble average over a suitable ensemble of matrix Hamiltonians of a given observable. Okay, I said D, actually. I said D will be the dimension of the Hilbert space, or let me call it the effective dimension. For example, the number of states in a given microcanonical window, e.g. size of an energy window. Okay. Now, the statement now, how this relates to chaos, is the following. So the spectrum of a chaotic quantum system with Hamiltonian H is statistically equivalent to that of a random matrix theory in the correct symmetry class. So you have the spectrum of some physical Hamiltonian. I'm calling it physical Hamiltonian. Maybe this will become clearer as I go on why I say it like this, but this could be, for example, some chaotic billiards. So it would just be the Laplace operator on some interesting domain. But there is some physical system which has only one Hamiltonian, and the Hamiltonian is H, and this is what I call H physical. And it is, in a sense, statistically equivalent to the spectrum of an RMT Hamiltonian, where the form that this random matrix theory and therefore this integral takes is something that we will need to discuss. So basically the showcase example, or one way of saying what this actually means is that, for example, this is a statement about eigenvalues and eigenfunctions, but one particularly famous one is a statement about eigenvalue gaps. So if you look at some chaotic physical system and you record eigenvalue gaps between adjacent eigenvalues, so we have here omega, the difference of energies, and then we have some frequentist measure of the probability to find a given gap omega. So omega will be something like EI plus 1 minus EI in the system, and I want them to be adjacent. Then the statement is that this in a quantum chaotic system is actually equivalent to, is statistically equivalent to if I sampled these eigenvalue gaps from a matrix valued probability distribution, which actually in a case I will be more specific about can be done. For example, has been done by Wigner. This is why people refer to this as Wigner and Wigner-Dyson statistics. Something like pi s over 2 e to the minus pi s squared over 4. So there's a specific curve that actually can be predicted. And s, by the way, is just the difference omega measured in units of 1 over pi times the average spacing of eigenvalue gaps all over the spectrum. Okay, so to say it more, just to give you a little bit more details about this. So what are we saying here? What we're saying is we take some system, for example, one of those chaotic billiards, and look at the spectrum and make a list of all the gaps between eigenvalues, all of the eigenvalues, but they have to be adjacent to qualify to be a gap. And then assemble a histogram of how many times across the entire spectrum do you find an eigenvalue gap that is very small and a little bit bigger and bigger and bigger. And in fact, this maximum here occurs for when the eigenvalue gap is approximately the average eigenvalue gap. And what you find is that you can actually calculate the same quantity. In fact, I can write it out. You can calculate this. That will also be a nice exercise for you to do, actually. I'll maybe put it on the example sheet. But you can calculate these eigenvalue gaps now with respect to a matrix probability distribution, which, let me just say for now, Wigner simply guessed. But we can argue for this, and we will discuss in a little bit more detail later on in these lectures. But so you take something like the expectation over matrices, Hermitian matrices H of just the delta function that omega, that E I plus 1 minus EI has size omega over RMT. Actually, I should have written this in orange. This is what I thought. This gives you basically your probability distribution. and this is equal to P of omega. Now, this orange curve is known as Wigner's surmise because essentially he guessed it. Okay, and Wigner's surmise is actually what you get by saying, and what did I actually write here? I don't remember now. Did I write? I think I might have written the GOE one. If you say that your matrix distribution trace V of M is Gaussian, meaning it's e to the minus trace of the matrix squared, that it has time reversal, which means that you can actually look at orthogonal matrices, and then the E stood for the ensemble. And the statement is that this, on the order of just a few level spacings, if I look at the spectrum of a physical Hamiltonian and only on the order of a few level spacings, will be reproduced by the, let's say, histogram of eigenvalue gap distributions in this physical system. And so you can actually say that from a spectral perspective, the fact that E value gaps mimic Gaussian RMT is one definition of what it means for a system to be quantum chaotic. Now, we will actually discuss the Gaussian aspect of this, but for now, let's leave it there. And as I said, in Wigner's case, he really just guessed it. I mean, of course, Wigner was Wigner. He probably thought about it very carefully. And he probably also in his head had something like, well, what would be like the maximum entropy distribution that is compatible with having, like a Hermitian underlying quantum system that has time reversal. And actually, you can make this more formal. You can say, what is the matrix distribution that in an information theoretic sense maximizes the Shannon entropy, given that it has to be normalized matrices, and given that they have to be Hermitian and time reversal invariant, and you find the GOE, for example. But so now, okay, so let me make one more statement, because more generally, actually, you might not just want to showcase eigenvalue gaps. More generally, what actually you want to say is, what you actually want to say would be more something like, you take the density of eigenvalues, rho of E1, rho of E2, up to, you can actually take a K-level correlation of energy spectral densities. See, this is the generalization of the idea of looking at two eigenvalues. And also I'm relaxing the fact that they have to be adjacent. Okay, so I could, for example, I could have looked at rho of E1, rho of E2. Okay, this would be very similar to what I showed here, except that I'm not conditioning on these levels to have to be adjacent. And I can say that this thing, so the kth moment of the correlation between energy eigenvalues averaged over some window around some fixed microcanonical energy should be equal to rho of E1, rho of E2, rho of E K with respect to RMT in the correct symmetry class. So all spectral statistics, all the moments of the spectrum should be well described by a random matrix distribution. And let me say one last thing. Actually, I already almost said it here, but this is because it was mentioned earlier. Rho of E minus omega 2, rho of E plus omega 2 averaged, for example, in RMT, and then Fourier transformed as a function of time. That's actually the famous spectral form factor, which I don't know, Marine, I think, called it K of T. So the spectral form factor is a quantity that is sort of related to this eigenvalue Wigner-Dyson distribution, but it doesn't restrict it to be adjacent in eigenvalues. In fact, you can probe this eigenvalue correlation at different energy scales, and as a function of time, because of the properties of the Fourier transform, you actually see different energy scales manifest themselves. And in a quantum chaotic system, as Marine explained before, this actually leads to very typical behavior, including this ramp and plateau behavior at late times. Now, very good. So maybe I will, I don't know how much more time I'll go on a little bit. There are some things that can still be said without rushing too much. So one famous thing is that there is actually at least a conjectured way of connecting these sort of notions to the more classical notions that we started with. And it's the famous conjecture of Bohigas, Giannoni, and Schmidt, which is that if you take a classical system that is classically chaotic, then its semi-classical quantization, or let's say its quantization, satisfies these spectral notions. So there is BGS, it's known as BGS conjecture. So the spectrum of a physical Hamiltonian with H physical corresponding to a classically chaotic system basically its quantization shows RMT chaos. And well, first of all, this is a famous conjecture, so it's good to know it. I will also make references to it later on when I talk about gravity, but actually, as it also been already sort of understood this morning, apparently there exist also exceptions, but exceptions, of course, will have to address the hypothesis of this conjecture. And trying to understand, for example, the ways in which you can have exceptions or cases that are between the two behaviors is precisely also where the interest lies. Okay, so now I think maybe I'll take 2 more minutes, or is this a good time to stop? Let me take these 2 more minutes to say the last thing, which is I will take this up again this afternoon, but there is the second set of natural quantities that are present in a quantum theory, which is the matrix elements of operators. And we can talk about quantum chaos also there in the context of the so-called eigenstate thermalization hypothesis. And the eigenstate thermalization hypothesis is often formulated as saying that if you take a non-extensive operator A, so think of it as either a local operator in a system that has locality, or a small operator in a system that has no locality or approximate locality, then there is a way that these matrix elements can also be thought of statistically with respect to the ensemble of eigenstates and eigenvalues along the lines that I treated here. And statistically, I can think of this as given by essentially 2 contributions. You have a smooth function of the average energy of these 2 levels. So E bar is half EI plus EJ for 2 energy eigenvalues. And these are located along the diagonal in the energy basis. Plus, you have entropically suppressed off-diagonal values, which are modulated by a continuous function of the average energy, and the difference of energies, omega, is AI, EI minus EJ, times, and here we come again with a random matrix. So this is the last thing I will write. What we have here is we break too many of these chalks, Gaussian question mark random matrix. So random matrix theory also will make its appearance. I will say more about this afternoon. but when we talk about the other aspect of quantum systems, namely its operator matrix elements. Let me just conclude by saying that, just emphasizing again, this is like makes reference to a small subpart of the system, and I and J should be, in some sense, highly excited eigenstates, meaning eigenstates that are so excited that in the thermodynamic limit, they lead to a finite energy density of the system. So there is also some hierarchy between what you are allowed to measure and the rest of the system. Okay, so I'll stop here, and of course I'm open for questions.
Is there any physical reasoning or some understanding of why that statement should be true? That the spectrum of H physical, which is quantum chaotic, should be like the thermometric spectrum?
There is. I mean, there are many people who are more expert at this than me, but my own thinking about this, and maybe small contribution, is that there are ways of understanding, for example, this random matrix type physics as actually just an effective field theory, a particular effective field theory. And so then effective field theories sort of describe universal physics that emerges independent of the microscopic details. And so you can actually understand, not with mathematical precision, by the way, in the sense of like proving an actual conjecture with precise hypotheses, but you can understand it to some physics level of let's say, argument that this effective field theory emerges typically in a chaotic system. And you reformulate basically all the predictions of random matrix theory in terms of this effective field theory, and then the question is just a statement about under what conditions do you expect this effective field theory to emerge. But of course, if that were an actual proof, then this BGS conjecture would no longer be an open conjecture. In fact, some people have gone quite far in using sort of semi-classical analysis and this emergence of this effective field theory through a semi-classical analysis to establishing this conjecture. But again, I think it's not thought to be a mathematically speaking resolved problem. And of course, what's going on nowadays is that people are seeing many chinks in this, like many more interesting exceptions, not just this arithmetic chaos, but also the emergence of things like quantum scars, or, you know, so it's a very detailed topic. So it's also not always obviously true in this most general form.
And maybe one more question. So is it necessary when we talk about BGS conjecture to have a reference to classically chaotic systems?
Yes. I think that's what it's formulated as. But I think Thomas is much more expert on this.
Yeah, I will talk about it. You can go beyond.
Question?
Yes.
Is there a generalized formulation for infinite dimensional systems? I mean infinite dimensional Hilbert spaces, because
Very good.
some
No, not as far as I'm aware of, except that in such systems, again, you can effectively go to some window of energies, like a microcanonical window of energies, which would be finite, and then apply the techniques in such a window. But of course, a lot of the late time phases of this ergodic behavior is just trivial for systems that have infinite dimensions in your sense. So it's also not always an interesting question.
You mentioned appropriate symmetries.
Yeah.
Is there any restrictions on what those might be described by?
Yes, actually, there is a full classification of these symmetries. There are 10 symmetry classes, and they go under the name of Altland-Zernbauer, but should probably have many more names. The original ones, the first 3 symmetry classes, which are the unitary, orthogonal, and symplectic ensembles, were already worked out by Wigner and then Dyson. And it turns out that there are 7 others, and they have to do with the presence or not of 3 anti-unitary symmetries in the system. But as I said, so I can write it, and I think in my notes, if you want, I can put the full table, but they are known as the Altland-Zirnbauer or AZ classes. They're also, this is a very prominent set of symmetry groups which arise actually all over the place because they're related to a very robust mathematical things like Bott periodicity. So they also come up, for example, in this table of elements of topological insulators, and they're just sort of very, maybe an attractor point of analysis of discrete symmetries in physical systems. But there's 10 of them. I should say that I don't think I will have time, but some in recent years, myself and some collaborators have done work which is totally motivated by gravity, but we try to reconcile these kind of things with, for example, CFT symmetries. And we find that in some sense in these field theories, of course, Altland and Zirnbauer never made a statement about field theories, but in field theories you have to kind of go beyond these also.
Is there any parallel with mixing the Gauss theorem, something like, can you understand how...
Like a quantum ergodic theorem.
Derives from another?
I don't know. I think the answer currently is no. But again, Thomas might talk about this. I'm not sure. Some quantum ergodic theorem type thing. But it's an extremely interesting question, let's say it like that. Okay, looks good to me. See you this afternoon.